So recall our diamond data set from before. Here y was the price and x was the caret. Consider now trying to fit a line through this data where we have both an intercept and a slope, so a two-parameter regression setting. And of course we wouldn't want to fit a line through the intercept in this case because look, it should go somewhere around 200 for the y point. So we definitely don't want a line through the intercept. We simply want to find the best fitting line through the data like that. So we want to minimize y minus beta naught times jn plus beta 1 times x, where jn is the vector of 1s, so that's just 1, and x is caret, the weight of the diamond, basically. So how can we do this? So far, we've actually derived a matrix version of this in a previous lecture, but let's go through it as a two-parameter problem here. But first, before we discuss the two-parameter problem, let's talk about what we're doing relative to projections. So imagine, in this case, y isn't three-dimensional. Y is however many points that is dimensional, 20 or something like that. But imagine if y was three-dimensional. We only had 3 data points. What would we be doing? Well, our vector y, our outcome, would be a point in three-dimensional space, right? And so our surface would be all the points that we want to project on would be all the points that are of this form as beta naught and beta 1 vary. So that's a plane in 3 dimensions, right? Because it's inherently two-dimensional, right? Only 2 parameters are varying linearly in that space, the space that looks like this, the space gamma, which is the collection of beta naught times jn plus beta 1 times x for beta naught, beta 1 in R2. That space is, of course, two-dimensional, so it looks like and it's linear, so it looks like a plane in 3 dimensions. So what we're trying to do is, given our outcome y, which is right here, we want to project it onto this two-dimensional plane and find the point, let's call that y hat, the point that lives in that two-dimensional plane that is closest to the observed data y. The specific values of beta that multiplied times jn and x to give us that point y hat are going to be, we'll call those beta naught hat and beta 1 hat. So in this lecture we're going to talk about how do you find beta naught hat and beta 1 hat. Another way to think about this problem is to think in terms of the scatter plot where we have y and x. Here we have a line of the form y equal beta naught plus beta 1 x, and our least squares criteria is taking the vertical distances between the points in the line and finding the line that minimizes the sum of the squared vertical distances. So that's another way to think about it. So there's 2 ways to think about it. One is to think about it as minimizing the vertical squared distances from the scatter plot, and another is to think about it as a projection in n-dimensional space. Of course, we can't visualize the n-dimensional projection. We have to think of it, pretend like it's a 3-dimensional projection just for the illustration. So let's go ahead and do this, and I think there's a pretty easy way to do this with the tools that we've already built up. So consider y minus beta 1x minus beta naught times jn squared. Imagine if beta 1 was fixed. So let's just think of that as a single vector. Okay? Imagine if beta 1 was fixed. Then the minimum of this equation over beta naught is just going to be the average, because this is just regression with a constant. Okay? It's going to be the average of this vector here. Okay, so the average of that vector there is just jn transpose, 1 over n jn transpose times y minus beta 1 x. Okay, but because of transitivity, this works out to be 1 over n jn transpose times y, which is y bar, and minus beta 1, which is scalar, times 1 over n jn transpose times x, which is x bar. So we know that the minimizer has to go through the point y bar minus beta 1 x bar. So that's our intercept, beta naught hat, as it depends on beta 1, has to be equal to that. So let's plug that back into our equation. So y minus beta 1 x minus beta naught hat of beta 1. So we're going to plug in y bar minus beta 1 x bar times jn, okay, squared. So we know that this quantity right here, asterisk, that asterisk has to be greater than or equal to that thing. Okay, so let's just do some reorganization. Okay, so this works out to be y minus y bar times jn minus, so that takes care of that term, then the y bar times jn, and then we need a minus beta 1 x minus x bar. Forgot my jn. X bar times jn. Quantity squared. Okay? Now, before, whenever we centered our random variables, we were calling them y tilde or x tilde. So notice this is just the centered version of y, and this is just the centered version of x. So this is now equal to y tilde minus beta 1 x tilde squared, where y tilde is simply y minus y bar times jn, and x tilde is equal to x minus x bar times jn. Now, this equation is exactly regression to the origin with the centered variables, which we talked about in a couple lectures ago. So we know that beta 1 hat has to be equal to the inner product of y tilde and x tilde over x tilde, inner product of x tilde by itself. And we also argued that that worked out to be the correlation between y and x, the estimated correlation between y and x, times the estimated standard deviation of the y divided by the estimated standard deviation of the x. So the regression, the best regression slope works out to be exactly the same slope as if we centered the variables first and then did regression to the origin. And the intercept, if we needed an intercept, right, so that's beta 1 hat, and if we needed an intercept, beta naught hat is just y bar minus beta 1 hat x bar. And so we've proven by plugging these in that we've gotten as small as you possibly can in terms of the set of inequalities, so these must be the minimizer of the least squares equation.